welcome back again. I think I just kept you out in the same clothes because it's still the same day. Or maybe I don't change them anyway. Okay, so we're moving towards the end of chapter 2, end of chapter 10 on fields, but a pretty big and important section looking at satellite motions, or spacecraft, probably satellite motion would have been a better one. Okay. So we're talking, last lesson we were very much involved with the electric fields. This one is very much gravitational fields. So let's just go through those main formulae again. So the gravitational force is GMM on R squared or D squared or X squared. The gravitational field is F over M. And again, these linking formulae, remember those. Don't just throw them away. Remember how we get to each of these. Gravitational field is the force per unit mass. So it's GMM on R squared divided by M is GM on R squared. Note that force and field are both vector quantities. Potential energy is the work done. It's the area under the force distance graph. It's the integral of FdR. The integral of FdR, so it becomes negative GMM on R, and the potential, Vg, gravitational potential, as opposed to electric potential, is equal to the potential energy per unit mass, so it's this one divided by m, so it becomes negative Gm on R. Both potential energy and potential are scalar quantities. These two here, F and EP, they depend on m, or they depend on what's actually put there. So what's the force on this mass? Well, it depends what the mass is. What's the field at this point? Well, that's 9.81 or whatever it is. What's the potential energy of this mass? Well, it depends what's put there. What's the potential at this point? Well, it's so many joules per kilogram. So force and potential energy depend on what's put there. Gravitational field and potential are something which is specific to that point in space. It doesn't matter what we put there. Hence, potential energy is m times whatever the potential is. Force is mass times whatever the field is. Field is the negative potential gradient. That sort of comes into this section a bit. So that means that the field G, and you might say, hang on, G is just 9.8. G is 9.8 out or near the Earth's surface, but G is also used to stand for the gravitational field around any planet at any point, and so it's going to vary. And so that's the negative potential gradient, the change in potential over the change in position. And a very common one, I'll write this out in a moment, but the potential might be negative. And if it was the potential between two equally charged, equal masses, then we'd get something like that. And at the point at the top here, the gradient is 0, so the gradient of the potential graph, if the gradient is 0 here, then that means that the field is 0 there. That means that the force is 0 there, so we're in equilibrium, we're at a balance point, we'd experience weightlessness at that point. If the masses weren't equal, then we might get an asymmetrical one like that. And at this point here, where the gradient is 0, that would correspond to the field being 0. Okay. Alright, so let's look specifically with rockets and you've all heard the term escape velocity, or really escape speed. Okay. So, when we're at the Earth's surface of any planet, the potential energy is negative. Remember that potential energy is defined as 0 at infinite separation. EP grav is defined as 0 at infinite separation. So it is negative at any finite does escape velocity mean? Or escape speed? It means how fast we've got to fire something up in the air so that it can escape totally. Sort of two concepts of it here. It takes a certain amount of energy, a certain amount of speed to put something into orbit, and it takes more energy to get it beyond orbit and out to infinity. All right? So, if we've got a mass m on the Earth's surface, whether it's a rocket or whether it's David, which David? One of them, then we would need to throw or shoot David with a pretty high speed to get him out to infinity. How fast? So if we want to get it to infinity, we want to get to infinite separation. Where's infinity? It's not a place, but as we get further and further and further away, we're getting close to infinity. And as we get further away, the EP becomes 0. So we want it to get there. If we want it to just get there with nothing left over, then we want its potential energy to be 0 and its kinetic energy to be 0, so we want its total energy to be 0. Total energy equal to 0. Surely one of these pens works. So we need to give it as much kinetic energy as its potential energy is negative, so that its total energy is 0. So that means a half mv squared has to equal g m on r. Okay. The m's cancel out. It's interesting. What that means is, it doesn't matter how heavy the mass is, whether it's David or a stone or a huge rocket. Clearly we need a lot more energy to put the rocket out to infinity, but we don't need any more speed. It's still got to reach the same speed. So from that we get that v squared equals 2gm on r. V equals square root of 2gm on r. Well, let's chuck in some numbers. At the Earth, v equals square root of 2 times g. You're not expected to know, but 6.67 by 10 to the minus 11. Mass of the Earth, 6 by 10 to the 24, over radius of the Earth, 6.4 by 10 to the 6 metres. And again, you're not expected to know those numbers, and obviously g, the gravitational constant, is given in your data booklet. I'm not sure if the mass of the Earth, radius of the Earth are, but there are things. I was marking some stuff last night, and finding the specific heat capacity, latent heat, I think it was, of water. Right, and if you remember that, then when you get your answer and it's close to it, then okay, good, I'm happy with that. When you get your answer and it's 3 orders of magnitude out, forgot to change grams into kilograms. So, if you just got some of those numbers in your head, then you can sort of look at an answer that you've worked out and say, oh yeah, that seems reasonable. They might give you a question to work out from this, work out the mass of the Earth, or more likely, another planet. It might be Mars, it might be Jupiter. Oh, I don't know what the mass of Jupiter is, I don't know what the mass of Mars is. I know that Mars is a bit smaller than the Earth, so again, I'm not sure what it is, but I'm expecting the mass of Mars would be low by 10 to the 24, or something by 10 to the 23 maybe. The mass of Jupiter, from memory, I think the Sun is 1,000,000 times heavier than the Earth, so we're looking around about 10 to the 30 kilograms for the Sun. I reckon Jupiter, or Saturn is probably somewhere in between, somewhere around about 10 to the 27 kilos. And I might get something by 10 to the 26 or something by 10 to the 28, but at least that's reasonable. If I get something by 10 to the 51 or 10 to the minus 12, then I'm going to recognise that as a mistake. So just to have a bit of an idea of those numbers. I haven't got my calculator here, but I'm pretty sure that comes out to be 11.2 kilometres per second. So 1.12 by 10 to the 4 metres per second, something like that. And so that's the escape velocity from the Earth. By all means, check those calculations, and hopefully that's what you come out to get. All right, and so that doesn't, it doesn't matter what the mass is. So anything, if Konica starts running and reaches 11 kilometres per second, then, well, in fact, as we'll find out, it would be less than that, and she'd start just going in orbit around the Earth. Of course, she'd burn up before she got to that situation. Okay. Let's go back over to that side. Didn't do much space there, did I? For a satellite in a stable orbit. So what we've worked out before here, you've got that interchange between potential energy and kinetic energy. For a satellite in a stable orbit, it's in a very specific situation. In order to be in a stable orbit, it must have a certain kinetic energy, it must be at a certain position. It's, is it in equilibrium? What does equilibrium mean? Equilibrium means no net force. Well, there is a net force on this because it's accelerating around the Earth. So it's not, a satellite's not in equilibrium because it is accelerating. Okay? So for a satellite in a stable orbit, here's the Earth, fairly odd-looking Earth. Here's the satellite going around. Okay. What force or forces are acting on the satellite? Pause it. Tell me what force or forces, think about what force or forces are acting on that satellite. Pause it, think about it, now come back. Welcome back. Did you go away? Alright. The only force acting is the gravitational force. F equals, I've just rubbed it out, G M on R squared, D squared, I'm going to call it R squared. Careful using R. R is not the radius of the planet, R is the radius of the orbit from the centre of the Earth. Sometimes they'll trick you and say we're so many kilometres above the Earth's surface. If we were 2R above the Earth's surface, then we're 3R from the centre of the Earth. So just be careful of that. Okay. That force is acting on the satellite, it's causing it to move in a circle at constant speed, i.e. it's causing centripetal motion, therefore it is the centripetal force. It is the centripetal force. It is causing the centripetal motion. It is causing the centripetal acceleration. So Gmm on r squared equals mass times acceleration. Mass times v squared on r, or m times 4 pi squared r on t squared. We could use either of those. So m times v squared on r, F equals ma. F equals ma. That bit there, let's put a box around it. Any question involving satellite motion, orbital motion, that's your first step. F equals ma. The force acting on it is the gravitational force. That will equal mass times the acceleration. F equals ma. Okay. So from this, I've got that expression. Where am I going with this now? Let's, so, is there a room? I mean, there's a lot of places we can go from here, but you know, what I want to do is look at the energy. If I divide both sides by, multiply both sides by r, so I'm getting rid of an r on the bottom. Gmm on r is equal to mv squared. Well, that's almost kinetic energy anyway. Divided by 2 Gmm on 2r is equal to a half mv squared, which is equal to Ek. The negative Gmm on r is equal to the Ep. Therefore, Ek equal to negative a half of the EP. Ek is equal to negative a half of the EP. When the satellite is in orbit, it has a certain amount of potential energy, negative Gmm on r. And the kinetic energy that it's got at that point is positive Gmm on 2r. So it's got negative 100 joules of potential energy and positive 50 joules of kinetic energy if it's in a stable orbit. If it's racing towards Earth or racing away from Earth or whatever, then it can have as much kinetic energy and potential energy as it wants. But if it's in a stable orbit, then its kinetic energy will be a half as much, and the opposite sign. Obviously kinetic energy can only be positive compared with the potential energy. Right, now that leads us to some pretty interesting bits. So kinetic energy is negative a half of the potential energy. Put a box around that one as well. Total energy is the kinetic energy plus the potential. So it's a half mv squared plus negative Gmm on r. But a half mv squared was Gmm on 2r, so it's Gmm on 2r minus Gmm on r equals negative Gmm on 2r, which is negative Ek. potential energy is negative GMM on R. So it's going to look like this. So it's a 1 on R type graph. If I was drawing a 1 on R type graph, sometimes we're not sure, is it a 1 on R or 1 on R squared? I try to make equal divisions there. I'm going to have this point here on my graph. If it's a 1 on R, by the time I go to double the distance, it's going to be half as much. If it was a 1 on R squared, by the time I go to double the distance, it would be a quarter as much. At half the distance here, it's going to be 2 times as much. So something like that. So a 1 on R squared is going to be a lot sort of sharper and deeper into the corner. So this is something like that. So this is the potential energy. As we get closer and closer to the Earth's surface or the planet's surface, whatever it is, the potential energy is getting more and more negative. Okay. Kinetic energy is negative a half the potential energy. In a different colour. Kinetic energy. So we've got this much negative, we've got half as much positive. We've got this much negative, we've got half as much positive. We've got this much negative, half as much positive, and so on. This is the EK. Alright, so for a satellite in a stable orbit, as we get closer and closer to the Earth, its speed will increase, its kinetic energy will increase, so its speed will increase. Total energy is EP plus EK. Total energy is the opposite of EK, so it's going to be in the middle here. I'll do that in black. So something like this, something like this, something like this, and something like this. Not very well drawn. That's the total energy there. So, as a satellite, satellites are whizzing around up there, there's lots of them, above the atmosphere. Well, where's the top of the atmosphere? It's very easy with the top of the ocean. You've got an ocean of water and then you're above the ocean of water. But an ocean of atmosphere, it extends, how far? The top of Everest is about 8,800 metres. You've still got atmosphere there, not much. It's thinner and thinner and thinner and thinner and thinner. So that's Everest 10 kilometres, say. 20 kilometres, you certainly couldn't survive. Planes are usually flying at about 10,000 kilometres around the top of Everest. But at 30,000 metres, 30 kilometres, you're getting very thin. It just gets thinner and thinner. So, probably 30 kilometres, you can consider as the top of the atmosphere, but it's not really, because it just keeps on getting thinner and thinner. And so the satellites, are having occasional collisions with particles, and even the ones, certainly the ones that are tens of thousands of kilometres, above, or hundreds or thousands of kilometres above the Earth's surface, are well clear. And some very special satellites are geosynchronous ones, geostationary ones, which have got an orbital period of 24 hours, and we can work that out using this one. GMM on R squared equals m times 4 pi squared r on t squared. And with a period of 24 hours, obviously the seconds, it comes out to be, God, I can't think of it. 36,000 kilometres above the Earth's surface, so about 43,000 kilometres from the centre of the Earth. That's about right. It's around about 6 times the radius of the Earth. Well, satellites up there, are well and truly clear of any of the atmospheric effects, but the much lower satellites that are going around, the surveillance satellites, are just above the atmosphere basically, and so they do lose a bit of energy because they have collisions. If they lose energy, it's the total energy that decreases. So that means they move from here to here. Alright? They lose some energy because of the friction with the particles. Thermal energy is given off to the particles, they lose energy. Alright, so what's happening? We're coming from here to here. We're coming from here to here. So as they lose energy, the potential energy will get less. They'll get closer to the Earth. R instead of, way out here, comes back a bit. So they'll get closer to the Earth. No surprise there. As they get closer to the Earth, their potential energy becomes more negative. Their kinetic energy, becomes more positive. So that seems a bit of a contradiction, that due to friction, due to energy losses, the speed's going to increase. But that's what happens. Okay. Alright, what else do we need there? I've got a nice graph there, exactly the same as what I had. Different types of orbit. Okay. Alright, let's just talk about those then. Seems pretty obvious, and yet, they've certainly tricked people in the past with this. So, here's the Earth, here's the axis of the Earth, here's the equator of the Earth. So, we can have a satellite that's in orbit around like that. We can have a satellite that's in orbit around like that, and we can have a satellite which is in orbit around like that. But I'm drawing in red the one we can't have. Most of the Earth's population is in the northern hemisphere. Well, is that true? Yeah, China, India, certainly most of the first world countries. You've got a lot of people in Africa and South America, I guess, but even then, there's a lot of Africa in the northern hemisphere, there's a lot of South America in the northern hemisphere. And no doubt it would be very useful to have a satellite that would go around like that. And you might think, that's got the centre of the Earth, that's the centre of its orbit, you've got the axis of the Earth at the centre of its orbit. But as it goes around, the direction of the force is not in that direction, it's in that direction towards the centre. And so that's not a possible one. Okay. So again, they can trick you with that. Lots of satellites are going around above the equator. We get ones like that which are oblique. We also get these circumpolar ones. Circumpolar. And basically they're going round and round and round, and the Earth is rotating underneath towards, well, if this is the North Pole, it's the South Pole, it's rotating towards the east. That's why the sun rises in the east and sets in the west. So that's the sort of satellites that we can have. Many satellites are in low orbit. Most satellites. lowest is 100 kilometres above the surface. I'm not saying somewhere in lithium. Two different types of orbit. They've seen 200 kilometres. Yeah. Satellites can be put into orbit at any desired height above the Earth's surface, assuming they're high enough to avoid air resistance, above approximately 200 kilometres. Okay. Orbits that are closer to the Earth have obvious advantages, especially if the Earth serves being monitored for some reason, to look for spies, to check out students who aren't doing their homework. We could have a satellite going ahead and see, for example, that Phys was playing computer games instead of doing his physics homework. Satellite going overhead, checking on Phys. I think he probably would be doing his physics homework. Most satellites are in a low orbit. It means that they're closer and they can see things. So let's say usually about 200 kilometres above surface. And that's not the radius of the orbit. The radius of the Earth, the radius of the orbit is the radius of the Earth plus 200. Therefore, the radius of orbit equals RE plus 200 equals 6,400 kilometres plus 200 equals 6,600 kilometres. Okay. Let's work our way through this. Okay, so back to that original formula, F equals ma. That's what you are applying. That's your first step. F equals ma. Gmm on r squared equals m times 4 pi squared r on t squared. F equals ma. The one we used before was F equals m v squared on r. Okay, that's your first step. Now, what do I want to find? I haven't asked the question, but I want to find what the period is. So I get, first of all, again, the masses cancel out. I get that t squared over this side equals 4 pi squared r cubed over gm. T squared equals 4 pi squared times r cubed. That's 6.6 by 10 to the 3 kilometres, so 6.6 by 10 to the 6 metres. I want that cubed over g, 6.67 by 10 to the minus 11 times mass, 6 by 10 to the 24. So t equals, work that one out, work it out. I reckon you're going to get, it's something like 100 minutes, right? When you get your answer, it'll be lots of seconds, so let's say it's around about, so we'll say 100 minutes, so 60 to 6,000 seconds, which is approximately 100 minutes. So, I don't know what the lowest one might be 80, that might be more like 90 minutes, but it's somewhere around about that. So work it out and make sure, because there's a bit in that, t squared and r cubed, we've got t in seconds. And so what's happening with those satellites, whether they're circumpolar ones, and they are the most likely ones, because as the Earth rotates, I don't think I've got a globe here to show you with, but there's one up on the back shelf, but I'd have to wreck someone's project. As the Earth rotates, so this is going round and round every 2 hours, say. Right? And so as the Earth is rotating, we're getting, and you've seen this in some movies and so on. We can't see what those Chinese are doing, because the satellite won't be overhead for another 20 minutes, is what Mr. Trump is saying. Okay, so as the Earth rotates underneath, the satellite is going past, so the angle there is showing that the Earth is rotating around, and then down comes the next pass, and so on. So the satellites are covering, you know, so they're a certain distance above the Earth, you've got lots of them there, and so you wait until a satellite comes into range of that particular nuclear facility or that particular place that they're going to bomb, or, you know, I mean, it might be something to do with weather, so, you know, lots of different things. So you've got those ones there. I don't know what I was going to say with that, I'm sure it was something very important. But, you know, a more, not necessarily more important, a very significant one, geosynchronous. Synchronous, synchronise, same time, chronos, time. So geosynchronous means the same time as the Earth, means period of 24 hours. Geosynchronous period of 24 hours. So we could have a satellite going around like this with a period of 24 hours, but what we really want is one that's, you know, above the equator and going in the same direction as the Earth, which means it's always above the same position above the Earth's equator. Now it's some distance away, as we'll work out, but it's always in the same direction. And so if you live on the equator, it may be directly overhead, or if it's not, it's going to be directly east or directly west of you. If you are in the southern hemisphere, it's going to be in the northern sky, and depending on where it is, might be a little bit to the east or a little bit to the west. And if you're in the northern hemisphere, it's going to be a bit to the south, and again, maybe a bit to the east, maybe a bit to the west. But it'll be above the equator. And so, in order to make it geostationary, it needs to have a period of 24 hours and be above the equator and be travelling in the right direction. So, it's way out here somewhere and we're travelling in this direction. Now, just imagine if the Irish, no Irish ones out there, put one up there and said, right, not sure which way it's got to go. Is that not even an Irish accent? Sorry. And put it going the other direction. Then, you know, they'd be colliding into all these other satellites and people would not be happy. So, geostationary means period of 24 hours, above the equator, travelling towards the east. And is it travelling clockwise or anti-clockwise? Well, it depends which way you look at it. So on this diagram, we're travelling around like this, the arrow that's shown. When we look from above the North Pole, then it's going around like that, which I guess is anti-clockwise. If I look from above the South Pole, there's no reason why the South Pole should be at the bottom, just because Australia is there. But yeah, so to say clockwise or anti-clockwise can be a bit ambiguous and not clear, but you know, towards the east, I don't think that's ambiguous, I think that covers it. Alright, so what's that distance then? What's that, you know, so I want T equals 24 hours equals 24 times 3,600 seconds. So what we've got here from this formula, I'm going to rearrange that and get that r cubed. So I've got that r cubed equals gmt squared over 4 pi squared equals, again, 6.67 by 10 to the minus 11 times 6 by 10 to the 24 times 24 times 3,600 squared over 4 pi squared. And again, have a go at that equation. You need to be comfortable, you need to be confident and competent with using your calculator. All right? And so you will get questions like this, and if it takes you an extra few minutes to get that out, I'm not sure how I feed that in. There's some quite tricky bits there where you've got to find the cube root of the answer to that. So, I'm trying to think of the answer. I think it's 42 or 43,000 kilometres. So I'm going to say 43. So I think it's 43,000 kilometres. So 4.3 by 10 to the 7 metres, I think. Somewhere around about that. So when you work it out, you should get an answer something like that. Remembering that the radius of the Earth is 6.4 by 10 to the 6. That's around about 6 or 7 times the radius of the Earth. Alright? So that diagram, there's one radius of the Earth, there's another one, another one, another one, another one. I need to go out a little bit further to be a reasonable scale drawing of, but it's not terrible. Okay, the advantage of a geosynchronous satellite is, again, that it's always above the same point on the Earth's surface. So particularly for communications, for phone communications, for TV communications, so with your Foxtel dish, with your satellite TV, if the satellite was going overhead, then you'd need to get outside and move the satellite over. Oh, it's gone. No more TV. But the satellite is always above the same position on the equator, and therefore in the same direction. Now, where we are here now, north is in that direction. So if the satellite was above the equator on our line of longitude, then I just have to go like that. But it's no doubt a bit east or a bit west. And so, if all satellite dishes in the same city, in the same region, are pointing in the same direction. If you were on the equator, then depending on where it was, they might be, the satellite dishes might be very flat. And in my travel, I've been interested in that to see, when we were in Alaska, the satellite dishes were, almost vertical, pointing, so vertical, so that their axis was pointing almost horizontal, because it was a long way to the equator from there, and so therefore it was low in the sky to get to the satellite dish. So communications in particular, whereas the near ones are very useful for weather, for surveillance, and I guess surveillance is just a fancy way of saying spying. Okay, I think that covers chapter 10. Okay, we're getting there.